Hello and welcome to lecture 8 of the course Theory of Computation. In the past lecture 7, we saw the formal definition of NFAs. So NFAs seem to have more flexibility and power than DFAs. They seem to have, right? Because they have the capability of having multiple options from the same state, and if they see the same symbol, right? There is also the epsilon transition available to the NFAs. So the question is, can NFAs do something more than what DFAs can do, right? So that's a natural question because they seem to be more powerful. What, like for instance, can they recognize languages that DFAs cannot recognize? In this lecture, we try to address this question, right? And we show actually that NFAs and DFAs have the same power, at least in terms of the class of languages recognized, right? So which means that anything that an NFA can do, there is also a DFA that can do the same thing. Meaning, if there is a language that is recognized by an NFA, then you can also write a DFA for the same language, right? So there is no language that an NFA can recognize, but a DFA cannot, right? So towards this end, we need some basic definitions, and then we'll proceed to the proof, right? So we first define what we mean by equivalence. So two machines. So when I say machines, I mean computation devices like NFA, DFA, automata, right? We say that they are equivalent if they recognize the same language, right? And the main theorem that we'll see in this lecture is that every NFA has an equivalent DFA, right? So this means that so even in the last lecture I mentioned this. It is clear that a DFA can be viewed as an NFA, right? A DFA is already an NFA where we don't make use of the multiple outgoing, multiple arrows with the same symbol. We don't make use of the epsilon transitions. So a DFA is automatically an NFA, right? But then this statement shows that anything that an NFA can do, there is an equivalent DFA for it. This means that DFAs and NFAs have the same power, at least in terms of what languages they can recognize, right? So it is possible that like a language recognized by an NFA, if you write the equivalent DFA, it will have way more states than what the NFA has, and maybe the DFA is more complex than the NFA. But that is not the point here. The point is that anything that an NFA can do, a DFA can also do, right? But the resulting DFA may be more involved, right? That's which is not what we want to focus on, but this is something that I am just stating over here, right? And the corollary is that since any NFA has an equivalent DFA, what it means is that the class of languages that are recognized by NFAs is the same as the class of languages recognized by DFAs, and we already have a name for the class of languages recognized by the DFAs. The name is regular languages. So, right. So the thing that I want to say is that a language is regular if and only if there is some NFA that recognizes it, right? So this is a new characterization, an alternate characterization for regular languages. So far we have been saying that a language is regular if there is a DFA for it. Now we are saying that a language is regular if and only if there is some NFA that recognizes it. So notice both the directions of the statement if and only if. If an NFA recognizes it, we can make a DFA that recognizes it, so it is regular, right? If a language is regular, there is a DFA that recognizes it by definition of what the definition that we have already seen. And if there is a DFA recognizing it, the DFA is automatically an NFA. So if there is a language that is regular, there is an NFA for it. And if there is if the language has an NFA, by virtue of this theorem 1.39, there is an equivalent DFA, and hence it is regular. So notice how both the directions are taken care by this. Now what remains, which is not it's a bit long, is a proof of this theorem. Okay. So what is the idea? The idea is to, like we sort of saw the idea in the previous lecture, right? So the way we define the transition function of an NFA was something like this, right? The definition of the transition function was delta is q cross sigma subscript epsilon to the power set of q, right, which is a set of all subsets of q, right. So here itself we are the mapping goes to the subsets of q. So this is itself a hint, and we also try to keep track of the transitions of let's say of this particular NFA, right. So we try to see which states it can go to, right. So maybe let's try to see what happens here when this NFA or when this NFA sees the string which is 0 1 0 1. So it starts with q1. When it sees 0, it can only remain in q1, right, there is no other option. When it sees 1, there are three possibilities, right. It can go to q1, it can take the self loop to q1, or it can go to q2, or it can go to q2 and then take the epsilon, right. And then let us say the next symbol is 0. So if it was at q1, 0 gives you the option to remain at q1, and that is all. If it was at q2, there is this option of going to q3. If it is at q3, there is no next step available. So it is this path, right, this path kind of ends here. Okay. Now let us say the next symbol was this is 0. Let us say the next symbol was 1 again. So q1 1, there are three options, we saw that in the second step, q1, q2 and q3. And q3 1, there is only one option, which is to go to q4. So this is what, so this is where all the string can be, or where all the NFA can be after let me just correct this, after reading the string 0, then the string 0 1, then the string 0 1 0, and then the string 0 1 0 1, right. So so we are basically this we tried in the previous lecture as well. So now the point here is that what are we doing here? We are trying to see if the string can be accepted, and towards that end we are trying to see where all it can possibly go, and then we see that this string is indeed accepted because the accepting state is q4. So after reading 0 1 0 1, there is one way, right. So there is one way to reach the accepting state after reading this, so which is like this, right? The highlighted path is an accepting path. So the first 0 you remain at q1, the next one you go to q2, the next 0 you go to q3, and then the last one you go to q4, right. So this is an accepting computation path, right. So 0 1 0 1 is accepted by the NFA. So this is the idea that we try to do. So let's see how we will try to do this. So what we will try to do is we will try to keep track of sets, or the set of states where it could be, right. So what I'll try to draw the same thing in a different way. So upon starting, it can only be in q1, right. And so now I am writing it as collections. Okay. So when you see a 0 from q1, right, sorry, when you see a 0 from q1, sorry, you can only be at q1. So this 0 will actually take you to keep you at q1. If you see a 1 for instance, however, you could go to q1, q2 or q3, right, because 1 can take you to keep you at q1, or it can take you to q2, or you can go to q2 and then take the epsilon transition, right? Now from Q1, Q2, Q3, if you take a, if you have a 0, right? So from Q1, actually from this, the 3 states here. So for each of them we have to see. If you were at Q1, if you see a 0, you can go to Q1. From Q2, if you see a 0, you can go to Q3. From Q3, if you see a 0, there is nowhere to go, right? So there are only 2 next destinations possible if you see a 0. So which means this arrow leads you to Q1, Q3, this set, the set containing Q1 and Q3. Suppose you see a 1 from Q1, Q2, Q3, right? So Q1 itself, if you see a 1, you can go to Q1, Q2 or Q3. Q2, if you see a 1, there is no next step. Q3, if you see a 1, you can go to Q4. So if you see a 1 from here, you could be in any of these 4 states. Right? So the point I want to make here is that if you were in any of these 3 states and if you see a 0, the next time you can only be in these 2 states, Q1, Q3. And if you are in Q1, Q2, Q3 and then you see a 1, the next time you could be in any of these 4 states, Q1, Q2, Q3, Q4. So like that we can keep track of where all we can possibly be after that step, right? This is how we will convert the non-deterministic computation into a deterministic computation. So you try to keep track the set of all states that you can be, that we can be at after reading some part of the input, right? That's what we try to do here. And so the starting state will be the starting state of the NFA. So the starting state will be the set containing the starting state of the NFA, Q1. Now if you see a 0 here, there is no other state you could go to. But if you see a 1, the next state you could be at any of the 3 states, Q1, Q2 or Q3, which is what we have here, right? And like that I could write other states as well. So this is not a complete diagram. And then you accept if there is one of these, at least one of these states is an accepting state. So now you would accept the string 1 1 because 1 1 takes you from the starting state. This is the starting state, right? So maybe I'll just denote it separately. So this is the starting state Q1, and 1 1 takes you to Q1, Q2, Q3, Q4, right? And out of which Q4 is an accepting state of the NFAs. So this means there is a way to reach Q4 from Q1 upon seeing 1 1 in the NFA. So you would make this as an accepting state. So maybe I'll make it a double, right? So the point is you want to reach the accepting state of the NFA at some point. Okay, so this is what this is the rough outline of the proof. Now what remains is to make this more formal. Okay, so what we want to do, so let's break this down into 2 parts. First, we assume that the NFA has no epsilon transitions. Okay, so the NFA is only has one of the flexibilities, which is that there could be multiple outgoing arrows, right, for the same state. So some state is there which has, let's say, there are 2 outgoing arrows or 3 outgoing arrows with the same symbol. Okay. Now this is only flexibility. There is no epsilon transitions. Now we want to build. So this is the NFA, Q sigma delta Q0 F, and for that we want to show that there is an equivalent DFA. So we'll construct a DFA. We'll call it M. So M is Q prime, sigma, delta prime, Q0 prime and F prime. Okay. So everything, so the alphabet is the same, sigma. Everything else is, I'm just adding prime or dash to Q, delta, Q0 and F. Right. So now let's try to see what each of them are. Right. We have already kind of seen the idea. Let's try to formally write it down. So the Q prime, right, the set of states of the DFA. So at each time we want to keep track of where all you can possibly be. So we have already seen that the set of states of the DFA is the So each state is a subset, is a set of possible states of the NFA. So the set of states of the DFA is actually the P of Q, which is the set of all the states, or all possible sets of states. In other words, it's called the power set of Q. So each state of the DFA is a subset of the states of the NFA. So if the NFA has, let's say, 3 states, the resulting DFA will have 2 power 3 states, because that's the number of elements the power set contains. Okay. Sigma is the same, so there is nothing to say there. So I will start with the simpler things. So Q0, the starting state of the DFA, it is basically the set containing only the starting state of the NFA. Right. So you may be tempted to say that Q0 prime is actually equal to Q0, but this is not correct, because Q0 is not a state of the DFA. Right. The states of the DFA are subsets of the set of all the NFA states. So it is the singleton state containing only the starting state of the NFA. Right. Sorry, singleton set containing only the starting state of the NFA. So that is the starting state of DFA. So Q0 prime, the starting state of the DFA, is the set containing only Q0. Now the next thing is the set of accepting states of the DFA. So you want to accept a certain string, right? So you do some computation. Let's say out of Q1, Q2, Q3, Q4, like in the example above, Q4 is the only accepting state. Okay, Q4 is the only accepting state. So now, if after reading a string, you can end at Q1 or Q2, will you accept that string? The answer is no, because neither of them is an accepting state. Suppose instead of Q1, Q2, you also had Q4, which means after reading that string, you can end at 3 states, either Q1 or Q2 or Q4. Meaning there are valid computation paths that lets you end at Q1, lets you end at Q2, and lets you end at Q4. Now, will you accept this string? Of course, yes, because this means that there is a way to process the string ending at Q4, which is an accepting state of the NFA. Okay. So since there is one state which is an accepting state of the NFA, which is Q4, you would consider this set to be an accepting state. Right. So what I want to say here is that F prime is a collection of states of the DFA, but each state of the DFA is a subset of the states of the NFA. So let us consider one state. Let's say R is a state of the DFA, or is a subset of states of the NFA. Now, is this an accepting state? So it will be an accepting state of the DFA, right? So R is let's say R is Q1, Q2, Q4. Is it an accepting state? Yes, because it contains an accepting state of the NFA, right? So the way to say it is, there exists small r which is an R such that so maybe I will just shift this slightly, such that R is in F, where F is a set of accepting states of the NFA. Another way to say the same thing is, R is an accepting state of the DFA, right? So R is a subset of the states of the NFA. If, right, so we are saying that R contains an accepting state of the NFA. So another way of saying is that the intersection of R with the set of accepting states, right? So if you look at R and you look at F, there has to be at least one state or one common, there has to be some intersection between them. So this is not the empty set, right? So this is another way to say it. So R subset of Q is the same as saying that another way to say is this is R is in Q prime, because the members of Q prime are the subsets of Q, right? So this is another way of writing the set of accepting states of F. The next thing is it's probably the most involved of them all, is a transition function delta prime. So delta prime we have to define for a state of the DFA. So we are considering R as a state of the DFA. So R is a subset of the set of all states of the NFA, right? And a symbol A in the alphabet, right? This is what we have to define, where R is a subset of Q, where Q is a set of all states of the NFA, and A is a symbol of the alphabet. So maybe I'll just give a brief example. So let's say I have Q1, Q2, Q3, Q4, right? 0, 1, 0, 0. Let's say for good measure there is another 0 here. Now consider R to be this set containing Q1, Q2. Okay. Now in this case, what is delta of Q1, Q2? Sorry, maybe I'll just write it here below it. What is delta of Q1, Q2? Sorry, delta of Q1, Q2 upon seeing the input 0. Okay. So upon seeing the input 0, if you are at Q1, one option is you remain at Q1. One option is you go to Q2. Another option is you go to Q3. So you could be at Q1, Q2 or Q3. But if you are at Q2, another option is to go to Q4. So there are 4 options available. One is to remain at Q1, another is to go to Q2, another is to go to Q3, another is to go to Q4. What about delta of Q1, Q2? If you see a 1, if you are at Q1, 1 doesn't take you anywhere. If you are at Q2, 1 only takes you to Q1. So it is just a singleton set containing Q1. Right? So this is how you define transitions. So let us see how to more formally define it. Delta prime of RA, right? So there has to be so for each element of capital R, right? Let's say small r is an element of capital R. Let's say small r is an element of capital R. Now you want to see where all can you go from small r if you see the symbol A. So in the NFA, that is given by delta of R comma A. Right? So delta of R comma A, so where delta is the transition function of the NFA, tells you where all you can reach from small r upon seeing A. Right? And then you have to do this for each small r in capital R. Right? In other words, I want to do the following. Is a set of all states of the NFA which can be reached from R, from small r upon seeing A, for some small r in capital R. Right? So for some member of R, if A takes you somewhere, you include that. Another way to say the same thing is, consider all the delta RA, consider for some R. Now you take the union over all the R in capital R. This is another way to say the same thing. So this is the definition of delta prime. For each element of capital R, you see where all you can go upon seeing A, and you take the union. So this completes the definition of the DFA that is equivalent to the NFA that we started with, right? So we are not explaining, or we are not formally writing down the proof. The construction itself is fairly explicit, and it's fairly straightforward to see that the construction takes you to an equivalent DFA. Now notice that we made this assumption that suppose there were no epsilon transitions, right? So now we have to somehow incorporate this into the proof, right? So let's see how to incorporate this. So suppose you reach a certain, one of the places where it has to be incorporated is the transition function, right? So here we said that we go to all the state which can be reached, all the states Q, right? All the states Q which can be reached from any small r in capital R upon seeing a symbol A, right? But suppose you reach a certain Q, right? So what I am saying is, suppose you reach a certain Q, right? So R, and then you see an A, and you reach a Q. Now suppose there is an epsilon transition from Q that is S. Now you can reach S also, because from R you see an A, then you go to Q, then you take the epsilon transition and then you reach S. And suppose there is another epsilon transition from S and then you reach T, then we have to include that as well, right? So basically where all you can reach from Q by just using epsilon transitions, suppose there is another epsilon transition that is some other state, even this has to be included, right? So consider all the states that you can that you can reach, right? Just by using epsilon transitions, all of this have to be included. So for towards this end, we define what is called ER. Okay, that is a notational definition. If you ask me to name it something, I will call it the epsilon closure of R, because this is the set of all the states that you can reach from R by just using epsilon transitions, right? You may not use epsilon transition by using 0 or more epsilon transitions. So I am allowed to use 0 epsilon transitions, which means the states that are in R are included by default. So just to give a pictorial, suppose these are the states in R. Okay, these three are the states in R. Now this is an epsilon transition. Let's say this is a non-epsilon transition, and suppose this is an epsilon transition. Let's say this is something else, right? Suppose this has no epsilon transitions, right? Now so suppose this is R, right? Maybe I'll use the same color again. Suppose this is R, then the set of states that you can reach from R by using epsilon transitions are this is included, this is included, this is included, this is included, right? So these are the states that you can reach. Notice that this state over here, the one that I marked X, cannot be reached from the top state in R, like which I have marked as, let's say, Y, using epsilon transitions, but however it can be reached from, let's say, this one, the one that I am marking Z, using epsilon transitions. Hence X will be in the set ER. So ER is the one that I have drawn with the red outline. Okay. So anything that you can reach from R using epsilon transitions. When I say epsilon transitions, it could be no epsilon transitions also. So because of which the set ER contains R by default, because I have defined as the set of all states that can be reached from capital R using 0 or more epsilon transitions, right. So if I use 0, if I am only allowed 0 epsilon transitions, I can only remain at R. If I want to use one step of epsilon or more steps, then I will include other things that you can reach, right. So in this figure, whatever I can reach by epsilon, I have marked, right. So it depends on the case. So now this is the way to incorporate epsilon transitions into the proof. Suppose there are epsilon transitions. So we have to include the epsilon transitions. One way to do it is to include after each transition, right. So you try to see where all you can possibly go upon seeing a symbol, let's say A. Now if you see a symbol A, where all can you possibly go? Let's say you got a collection of states, right, which is given by delta prime of R comma A. This is a set of states. Now from this set of states, perhaps there are epsilon transitions that take you to some other places. Now we want to include that as well, right. So how do we include that? One way to include is by so delta prime of R comma A. So for each small r in capital R, for each small r in capital R, earlier we took for each small r in capital R, we took all the states that are in delta R comma A, which is the set of states reachable from R, small r in capital R, using the transition A. Now instead of delta RA, now we are saying, maybe I will use a different color here. I am saying E of delta RA. Similarly, in the union definition earlier, I just had the union of all small r in capital R, delta RA. Now from whichever states that you can reach from small r using the transition A, we want to add the other states that you can reach after the transition by just using epsilons, right. So if this is a set of states, let's say delta RA, now let's see where all you can reach by just using epsilons, right. So we want to include these as well. So now we draw a bigger circle, which is basically, this circle is E of delta RA, the set of states that you can reach from delta RA by using epsilon transitions, right. So this takes care of all the transitions. So after each transition, we are saying where all you can possibly be by using epsilon transitions. The one other place that we have to take care is so this is the transition function we have to modify. So instead of the 4 defined as the transition function being defined as this is the actual definition, right. And the other thing that we have to change is the starting state, because in the transition function we are accounting for the epsilon transitions after we make the transition. So what if the starting state had epsilon transitions, right? If Q0 had, let's say, 1 epsilon transitions, let's say Q1, how to include that? The one way to include that is to, instead of defining the starting state as just the set containing Q0, we can define the starting state as the epsilon closure of the set containing Q0. So again, this is a new thing. It is the epsilon closure of the set containing Q0. Right. So these are the two changes that we need to make if or for taking the epsilon transitions into account. So Q prime is a set of all subsets of Q, right, or the power set of Q. The starting state is the epsilon closure of the singleton set containing Q0. The set of accepting states of the DFA is a set of all is any subset of Q, which is a set of all states of the NFA, which has a intersection with the set of accepting states of the NFA, right? The set of all R which have a non-empty intersection with F. And finally, the transition function is given by this, right? For each the transition function from a set R upon seeing a symbol A. So you look at each small r and capital R, where all can you go upon seeing A? So that is given by delta RA. It is a set of states. Now you take the epsilon closure of it, meaning where all can you go after this by just using epsilon transitions. Now you take the union over all the possible R, small r and capital R. That is a transition function. So this completes the construction of the DFA. This completes the construction of the DFA that is equivalent to the NFA. So the correctness is fairly straightforward. So if you read any string, right, and the DFA reaches the states R1, R3, R10, right. So the DFA reaches the state R10. This means that the NFA, after reading the same string, can reach exactly these three possible states. It could reach R1 in the NFA, or R3 in the NFA, or R10 in the NFA. These three states are the exact states possible, right? And this is an accepting state if either three of them, or if any one of them or some subset of them is an accepting state of the NFA, right? So it's fairly clear by the construction that if the non-deterministic finite automata, the NFA can reach three states R1, R3, R10, then the DFA by construction will reach the state containing exactly these three states, right. So that is the main theorem that I want to state in this lecture, right. So the point is that computation power of NFAs is equivalent to DFAs, meaning in terms of what are the languages that can be recognized by the NFA, it is same as what can be recognized by the DFA, right. So this is proved by showing that every NFA has an equivalent DFA, and that is the construction that we saw. And the main idea is to build a DFA where each state of the DFA is a subset of the set of all states of the NFA. So one point is that this NFA has 4 states, right? The NFA in blue over here has 4 states. So the equivalent DFA as per this construction will contain how many states? So it will contain as many states as the power set of this contains. So the power set of a set of 4 elements contains 2 power 4, which is 16 states, 16 elements. So the equivalent DFA will contain around 16 states, one for each subset of this. So the set of states could be the empty, the set of states could be the empty set. It could be the set singleton sets, the set containing 2 elements, set containing 3 elements, and the set containing all the 4 states, right. So there could be 2 power 4, which is 16 states, and it can get a bit involved. Maybe one thing that can be done, that you can do is there is an example in the book, which is example 1.41, right. So the DFA that I have written below, which contains 3 states Q1, Q2, Q3. Q1 is the starting state as well as the lone accepting states, and it is over binary alphabet. So if you see, the alphabet is just A and B, and there is an empty transition as well. So for this state, in the Sipser book, they construct an equivalent DFA, and the equivalent DFA, as you would expect, contains 2 power 3, which is equal to 8 states. But then the example in the book notices that some states are not really useful, so they finally reduce. So the DFA, equivalent DFA, right, contains 2 power 3 equal to 8 states. Right? This is what we can say without any actual construction. But when you construct, actually there are some unreachable states, some states which are useless. So you can see in the example, they actually cut down 2 states because it is not serving any purpose in the DFA. So it ends up being 6 states. So please go through this example in the book, and yeah. So that's all I wanted to say in this lecture, where we saw the main theorem, which is that every NFA is an equivalent DFA, and also the implication is that this gives a new characterization for regular languages, which is that the regular languages are the class of languages that have some NFA that recognizes it. Right? So the earlier definition was that a language is regular if there is some DFA that recognizes it. Now I have a new definition: a language is regular if there is some NFA that recognizes it. Yeah, that's all I have for in lecture 8. See you in lecture 9. Thank you.